Our fission gas behavior is a whole animal on its own, so there needs to be some attention dedicated to this behavior. I'm taking most of my content from chapter 13 of Professor Olander's book. It is available in the PDF in the description. So previously we've been talking about radiation damage, and then we have covered up to the solid fission product swelling. So now we want to look at fission gas. Now for fission gas, upon generation, they'll be trapped like foreign objects inside the lattice. So let's say you have a relatively undisturbed lattice here, and then you have one atom of, let's say, xenon. So that's fission gas. Okay, so they'll be trapped like foreign objects inside the fuel lattice, and sometimes in the cladding too, since swift ions can ram themselves into the cladding. So you have fuel pellet here, and this is the cladding just on the outside. It's a cylindrical shape. Okay, so these two fuel pellets, some of the swift ions, it could be a xenon, it could be a krypton, they'll find themselves lodged into the cladding. After causing all the electronic stopping, pKa cascade, they'll rest in the region, and they'll be dispersed in the matrix of the fuel or metal. So for now, we want to focus more on the fuel. Since we've talked about the cladding already, so we want to look at the fuel, and that's where most of the action is. So we're going to look at the fuel, and we're going to see how the swelling and stuff occurs. So after knocking through lots of pKa's, xenon will rest in a, let's say, this is a fission fragment. Xenon will rest in a region with lots of vacancies. Why? Because when the xenon comes in to the lattice, it will make a displacement spike. So the pKa's will go here, then it will cause a displacement cascade, so that maybe here, the part I'm circling, they will have a displacement spike where there are high concentration of vacancies. Excuse me. High concentration of vacancies. So helium would have done the same thing as well. But in comparison to xenon, helium is relatively small because of the relative size of the electron cloud. Thus, the diffusion mechanism for helium and xenon will differ greatly. So here we'll start talking about xenon diffusion. And for this, we'll need some diffusion background, and videos are posted in the description if you need some prerequisite knowledge. So you need to know Fick's first law, second law, some mechanisms of diffusion, and know what diffusion is about. Now, all these videos will be put into the description. So, if you have xenon inside a uranium oxide lattice, so this is UO2, so there'll be something, I'm not drawing it accurately, but there'll be a fluoride structure. There'll be a fluoride structure where, let's say, a uranium ion is attached to two oxygens. So these are smaller ones, they're like oxygen. Okay? So xenon is a very, very, very big atom. And it's so big that it cannot just migrate through this uranium oxide lattice through a single vacancy mechanism. Okay, so what does it mean by that? Let's simplify again. We have a UO2 lattice. I'm going to just simplify just to how to say, just to help to illustrate the point. Okay, so you have these big ones that are uranium, and then let's say each of these uranium has 2 oxygen atoms attached to it. Okay, so this is a regular lattice. Now what will a vacancy look like? So maybe I'll take one of these away and 2 of these away. So, and of course this is not completely accurate. Okay. But now let's say there's a Schottky pair missing. And then there are some vacancies available. So this is something like a something like a vacancy. Okay, so these 2 are missing along with this uranium. Okay, let's say you have a xenon which is lodged into this vacancy. How is it supposed to move? Is it going to find, let's say, another vacancy here? So I'm going to just draw this vacancy. Maybe you have this 2. Okay. Is this xenon going to hop from this vacancy to this vacancy? Well, according to Professor Olander's book, the idea is that xenon is way too big for this to happen. So the way xenon has to kind of move around is that it must take the place of one uranium oxide pair. So 1 uranium and 2 oxygens. These will form a vacancy, sort of a cluster-like thingy. So it's a kind of a complex. So what you have is things like this. Okay, xenon will be trapped here, and unless there is a site, so let's say a vacant site here where the uranium and the oxygens are completely taken care of, or completely missing, only then that can a xenon hop into this spot, so to speak. And there must be enough space for this xenon to go through the whole thing. I mean, yeah, it cannot just be 1 uranium atom missing. It has to be 1 uranium and 2 oxygens missing. So there are a number of experiments to support this, but the idea is that you need one set of atoms to be missing for xenon to be moving around, rather than just 1 uranium atom missing or 1 uranium ion missing. Okay? Only then can xenon perform its random walk around the lattice. Excuse me. So, we have discussed that xenon can move around in the uranium lattice, and when one xenon finds another in the lattice, yeah, when one xenon finds another, they form a divalent pair. Now this xenon Xe2, they can form a nucleation site. So this is a nucleation site. They can form a nucleation site for a xenon bubble to grow. So once this xenon 2 is formed, when other xenon come in contact with it, they will start to join up more and more. And this is usually done, this usually happens in some kind of vacancy complex. So previously, we have one xenon occupying a space of 1 uranium and 2 oxygens. They're about that kind of size, that kind of a vacancy complex. So if you have a number of these kind of vacancy complex existing together, the xenons can join together. So maybe you have this side gone, and the xenon, extra xenon atoms can occupy into these sites. Okay. So sometimes this xenon 2 can combine with more and more xenon atoms to form a bubble. So in a bubble growth, first you have the nucleation step. Okay, so this is the nucleation site. Then you have growth. And so on. So xenon will join xenon 2, become xenon 3 xenons. So more and more xenon can form together when it joins together atom by atom. So that is the growth stage. And we have discussed that it's usually the xenon, single xenon atoms that are moving to join the nucleation site, or the so-called small bubbles. But can bubbles move as well? So can these bubbles move as well? Absolutely. And when the bubbles move, let's say XEN, so there's an n number of atom here. When this moves to make maybe XEM, so there's a m number of atoms here and n number of atoms here, and this bubble is moving to this bubble, and they have a new bubble, a bigger bubble forming. It's a bigger bubble. This is called coalescence. Now there are several mechanisms for bubble movement, and these are usually because of temperature gradients. There's a diffusion mechanism as well, and there's some stress involved. When stress, I'm talking about structural stress. Okay, but I won't elaborate on those. You can look at Professor Olander's book. But in essence, coalescence, this is coalescence will differ from growth, as for the first case, or rather the latter case, growth has individual xenon atoms moving, so the bubble kind of grows atom by atom. But after a certain size, when these bubbles are big enough, the dominant mechanism for bubble growth doesn't become this nucleation and growth anymore. What happens is that these things tend to join up to become bigger bubbles. This is coalescence. So bubble size tends to increase dramatically. So if we will have to have a plot of the bubble number density versus time, so it will look something like this. Okay, so it will start growing exponentially. So this is the number of bubbles per volume versus time. So at this stage, there's the nucleation phase and growth. Okay, so let me bring this up. Nucleation and growth. But after it bottoms out, it flats out, coalescence dominates. So these bubbles will start to grow bigger and bigger after a while. So how can we now start to take a look at swelling now that we have discuss some methods of how the bubble has grown. So let's consider doing some mass balance. And first, let's consider the bubble of a small size. Okay. So in our fuel pellet, we have a certain number of bubbles. And if you're talking about swelling, we are looking at volume change. So the appropriate quantity to look for is maybe a percentage. So the volume change over the initial volume. This is how we kind of characterize swelling. So if you find the volume of the bubble, or the total volume of the bubbles, how are we going to do that? And why is that important? Well, the final volume equals to initial volume plus total bubble volume. So we need to find this in order to find our delta V. So how can we kind of derive this volume? So we can look at it like this. Total bubble volume equals to the number of bubbles plus some representative size per bubble. And we look at some average size. So this is the number of bubbles times the average size of the bubble. Okay? So how can we find some representative size of the bubble? Well, firstly, we can do a mass balance. Okay, and once we have found the mass, we can relate the mass related to volume by some equation of state. And what's an equation of state? It can be like the ideal gas law, or it can. So in the equation of state, we can either use a van der Waal equation or simply ideal gas. So what is the difference between ideal gas and van der Waals? Van der Waals simply accounts for space taken up by atoms. And that sometimes plays a big role, especially when the pressure is pretty high. So let's continue with this approach. So first we want to do the mass balance. So in every mass balance, we can simply put it as such. Accumulation equals to gain minus the loss. So let's see for the gain term. Now let's consider the fission process producing the xenon. So we have xenon production rate, which is the xenon production over time. The xenon production over time is the fission rate times the yield of the xenon into time. And that, okay, this is fission per volume. Okay, so all of this is in a per volume kind of a number, a per volume basis. And this will be, okay, so when you produce xenon, some of it goes into the solid. So it's dissolved xenon in matrix of the fuel. So they are individually lodged in there. And this will be times the mass of each bubble times the number density of each bubble. So there must be some mass transfer from the xenon dissolved in the matrix into the bubble. And that requires some kind of other mass transfer. So for an infinite solid, okay, the MDT, which is the accumulation, that will be the J of the diffusion. This is the mass flux times the area, of course, of the diffusion. So that is going from the matrix into the bubble minus the flux rate from the bubble back into the matrix. So there are a number of things that can cause this to happen. For example, there may be swift ions that knock some of the xenon atoms back into the matrix, etc., etc., and there's diffusion that goes both ways. However, for design and introduction purposes, we are not so concerned with the mass transfer involvement in the rate of swelling as much as we are in the upper limit of swelling. So for simplicity's sake, what I'm saying is that the assumption is that this is all zero and all the xenon produced goes into the bubbles. So that ensures the maximum bubble size, and that helps us to account for how much swelling there is as a kind of an upper limit. So this is the upper limit of swelling. So Ray solution is 0, and there's another term that's I just call it leakage, but this is essentially the rate at which the bubbles or the xenon in the fuel exit the fuel pellet. For now, of course, I will say this is neglected. We'll just talk about an infinite solid as a limiting case. Okay. So we don't consider leakage as well. So this is a very what do you call this? This is a very simplistic way of putting it, so that we just find the upper limit. We are finding the upper limit of bubble size. So this excuse me, this will simply reduce to the rate of the fission gas being generated is the rate of bubble growth, basically. Okay, so we don't need to consider this anymore. We'll just consider this equation. So yxe into f into t equals to m times nb, where m is the mass of the atoms in each bubble, or the number of atoms in each bubble. Alright, let's go in right. And this is bubble per volume. Okay, so details for all the calculation can be found in chapter 13 of Professor Olander's book. So now we need an equation of state relating a bubble atomic density to the mass of the bubble. Okay, so yeah, we need to find this number, and we want to find we want to relate it to the volume, right? We need to find the volume. That's the end goal of the day. So to relate the number of atoms to the volume, that requires some knowledge of density. So rho of the gas. What is the rho of the gas? So the density again can be defined as such. This will be the mass over the volume, or rather the number density is as such. So number of atoms over 4 over 3 pi r cubed. So this is the volume of a spherical bubble, and this is the number of atoms in a bubble. Okay. And this will be atoms per volume. So straightforward enough. But the thing is that we don't really know, neither can we directly always measure the then bubble density or radius so as to find like kind of a bubble volume. And this is what we want to find anyway. And we can use micrographs and scanning electron microscope and all that, but we kind of want some knowledge of how this thing grows over time. Okay, and how much is the upper limit as a function of how much fission there is. So what can we measure? What can we measure? Okay, so we can measure temperature, or we can have a good estimate of temperature and to a lesser extent bubble pressure. So we need to relate all of this to density. Okay, so we can get bubble density so as to find the volume by going for this. Okay, let me adjust the camera. So okay, P 1 over rho G minus B equals to KT. So this is the van der Waal equation, where B is the term to account for the volume taken up by each atom. When that approaches to 0, when the volume per atom can be neglected, or volume taken up by each atom can be neglected, that will become the ideal gas equation. So this is the Boltzmann constant, and this is the temperature in Kelvin. So this will be on average about 85 angstrom cube for xenon. So this is 1 angstrom equals to 10 minus 10 meter, 10 to the power minus 10, and Boltzmann constant K equals to 1.38 times 10 to the minus 23. Okay. So temperature is straightforward, can measure or estimate that. But how about this pressure? How do we find that out? We have to do some force balance on the bubble, so we'll cover that in the next video. So thanks for watching, I'll see you guys there. Bye bye.